Well, welcome back. This is Unit 2. Now, I mentioned right at the end of Unit 1 we were talking about significant figures. So let's do a quick practice one. We won't have a straight review for your test as such. Basically, you're going to need to know everything that's on everything that I give you on the video is probably going to be on your test. And so take good notes as we go. So let's practice the significant figure one. So let's say we have something that's 65 grams and we're going to divide it by 5.156 grams. So when we put that in, we put that in our calculator, it's 12.6066718. And we say to ourselves, man, that looks really scientific, that's pretty good. But the problem is, remember, a chemist says I can only report what I know. And so when I look at this, I see that, oh, the lowest one has no decimal places, so my final answer has to have no decimal places. So since that is greater than a 5, that's a 6, so the answer here is going to be 13 grams. Okay. So I just want to tell you that you just take the one with the least number of decimal places, and that's what your answer has to be. And once again, the reason is we don't know if that was 65, if it was exactly, it would have been said 65.0, but instead we weren't able to measure it, so we don't know. It could have been 65.55589, whatever. So as a chemist, I know for sure that I've got this. Okay. Now, as we move in, let's talk about, we're going to talk about the periodic table a little bit. What's an element? An element is a substance that cannot be broken down into a simpler substance. The periodic table, these are all elements. Through the test of time, we found that they cannot be broken down into a simpler substance. Sodium Na is always sodium. And keep breaking it down into smaller pieces, it's always sodium. And so forth. We go through the deal. Gold is an element. Break it down, it's always gold. A compound is 2 or more elements. And then we know that we have 3 subatomic particles. We have protons that are positive, electrons that are negative, and neutrons that are no charge. So as we look at this and we have a nucleus, we have the protons and the neutrons inside the nucleus, and then of course the electrons orbit around the outside. Now, here's the neat thing. The neat thing is that, and this is probably a review for you, you've had this before, but protons have a positive charge and electrons have a negative charge. Now, when we look at the periodic table, everything up here in its natural state has a 0 charge. Now, let's talk about why that is. The reason that is because we have something called the atomic number. When we look at the periodic table, in this particular periodic table, the atomic number, let me grab my meter stick here. The atomic number here is the number in the upper left-hand corner. Now, not every periodic table has that, but that's the atomic number. The atomic number tells us the number of protons and the number of electrons. So when I look at sodium, for example, the atomic number is 11. Now, there's really, you see all kinds of things on a periodic table. Sometimes there's all kinds of colors and different things. This is the periodic table that's accepted by the American Chemical Society, chemists like this, because there's very few things that we really need from the periodic table. We need to know where it's at, and we'll talk about that later in terms of groups and periods. We need to know the symbol, we need to know the atomic number, and we need to know the mass number. So the atomic number is never a decimal number, it's always a whole number. So zinc, for example, the atomic number is 30. So on the atomic number, we know the number of protons and the number of electrons. So let's go ahead and continue to look at zinc. So if we have zinc, chemical symbol, capital Z-N, it's an element, cannot be broken down into a simpler substance. And so it's 30. So that means that it has 30 protons, okay, or 30 positive charges, and it also has 30, because the atomic number is 30 once again, it has 30 protons, but it also has 30 electrons, okay? So what that means is that it has 30 positive charges and 30 minus charges for a net charge of 0. That's stable. That's stable. And I want to stress that because what we have to have in chemistry is everything is striving to be stable. Everything in the air is trying to become 0 charge. Everything wants to become stable. Nature will turn things back and forth until it becomes stable. When it's unstable, it's a problem. Everything on the periodic table in its natural state, in its free state, is a stable charge, which is charge of 0. Remember the atomic number, the number of protons, and the number of electrons. So now, if I begin to look at one-dimensional diagrams, okay, so this is kind of interesting because life is not one-dimensional. In a minute, I'm going to show you 3-dimensional, 6-dimensional, 8-dimensional. But as we begin to look at this, at first we introduce this, and we make this simple little diagram. and I really don't like this as a chemist, but we'll start from here, okay? So we look at sodium, okay? So we come up to sodium, the atomic number is 11. So I draw the nucleus here, okay? And I'm going to draw this one-dimensional little deal here, a one-dimensional deal for the electrons. So since it's 11, okay, I know that it has 11 protons. Okay, and it also has 11 electrons. The electrons travel around the outside of the nucleus. We'll talk about that later as well. So now the question is, how many neutrons does it have? Okay, so in order to get the number of neutrons, we subtract the mass number. We round it off. In sodium's case, it's 22.989. So we take the mass number, so that would be 22.9. So we're going to round that up to 23. Okay, so we take the mass number minus the atomic number, okay, so that would be 12. So we've got the mass number minus the atomic number, and that's going to equal neutrons, the number of neutrons. We'll talk more about why that is, but for right now, let me make this a little bit bigger so we can see it. So if we're going to draw sodium, okay, we've got 11 protons. Where did we get that? Oh, we got that from the atomic number right here, okay? Now, how many neutrons does it have? Well, it has 12. Where did we get that? The mass number minus the atomic number equals 12. And then we have the number of electrons. And where did we get that? We come up here and it says that the atomic number is 11, okay? And so that's the number of protons as well as the number of electrons. Now, I'm going to talk to you in a little bit about the three-dimensional model. This is a one-dimensional model, and that would be true if the whole world was on a sheet of paper. That would be true if we were all lived on a sheet of paper, but we don't. So I'll talk about the 3D model here in just a little bit. Well, let's look at another one really fast. Let's look at chlorine, okay? So we find Cl, we find chlorine over here, and its atomic number is 17, okay? So I want to draw a one-dimensional diagram of chlorine. So the first thing I'm going to do is I'm going to draw the nucleus here. So I'm going to say to myself, how many protons? So the protons are positive charge, and I look at chlorine, and the atomic number is 17. So I know that I have 17 protons. And then I'm going to draw the little track for the electrons around here. Okay, I say, well, how many electrons? Well, chlorine is atomic number 17, so I know it also has 17 electrons. Oh, that's cool. So now I've got to figure one more thing, the neutrons. All right, so the way to get the neutrons, I need the mass number minus the atomic number. The mass number. So I look at chlorine, once again, periodic table. I go to chlorine, and the mass number is 35.453. Now, I'll run around this up. Even though that's a 4, the next number's a 5. So let's look at that. So we've got, so here's the mass number for chlorine. I'll use this as a good example because this is kind of a tricky one. 453. So what I'm going to do is, even though that's not a 5, this 5 rounds that 4 up to a 5, which rounds this whole thing up to a 36. Oh, okay. So the mass number of chlorine is 36. The atomic number was 17. Okay. So, and I subtract those. And what do I get? Okay. So I have 19 yeah, I got ahead of myself there for a little bit. Okay, so I subtract those, and I have 19 neutrons. There we go. Got ahead of myself. Okay, so once again, the mass number minus the atomic number tells us the number of neutrons. So once again, one-dimensional model, as if we lived on a sheet of paper. Okay, as if we lived on a sheet of paper. Now, while we're at this board, okay, all right, once again, so the atomic number, protons, and the number of electrons. Okay, so we have some one-dimensional diagrams. Now, I want to go back and talk about some metric prefixes, so be sure you put these in your notes. Metric prefixes. All right. Once again, we work only in the metric system. So we have kilo. The metric prefix for kilo is 1,000. Okay. So if we have kilograms, okay, then we would have 1,000 grams. Centa is 100, 0.01. Milli, 1,000, 0.001. Giga is 1 billion. Okay. Now that's kind of interesting because when we talk about a computer, we talk about a gigabyte. Okay, well, it's really kind of fascinating because used to be we would type write things and we would talk about how much is on a page. Well, one single space page is a byte. So when we talk about a gigabyte in a computer, we're talking about the equivalent of a billion pages all typed up. So that's how we measure a computer, how much storage it has. So giga is a billion. Micro is 100,000ths. 0.0001, and then nano is 1 billionth. Wow. So what we're doing now is we're measuring things in nanoseconds. Can you imagine measuring something that says 1,001, break that down into a billion, and that's 1 nanosecond. And that's why we're beginning to understand chemistry and beginning to understand electrons. We'll talk more about nanotechnology as we go throughout this class. But these are the metric prefixes. You'll need to know those for your next test, as well as application for this class. Kilos 1,000, centa 0.01, milli 0.001, giga 1 billion, micro 0.0001, 100,000, and then nano is 1 billionth. All right, so let's go over. I told you we would talk about three-dimensional molecules here.